Good afternoon, ladies and gentlemen, students, the faculty members of computer engineering. Professor Kimura, are you here already?
Hello.
Yeah. So good afternoon, Professor Kimura. I'm sorry, I think I mute all. How to disable. So, Prof. Kimura, today's session will be hosted by Pak Igede Darmanograha. Pak Gede, are you there?
Yes, I'm here. Can you hear me?
Yeah.
Okay.
Okay, so I will give the host to Pak Gede how to do that. Right? Yeah, already give the host to Pak Gede.
Oh, thank you, Ms. Prima. Good afternoon, Prof. Keiji Kimura. Today, maybe I will represent the computer engineering of UI to be the host of this session. So maybe we can start for the session. So our distinguished guest, Professor Keiji Kimura from Waseda University, Dr. Aris Subiantoro, the head of Department of Electrical Engineering, Universitas Indonesia, Dr. Muhammad Salman, the head of Computer Engineering Study Program, and the faculty members of Department of Electrical Engineering and Computer Engineering of University of Indonesia. And also I would represent my greeting to the undergrad and grad students of Computer Engineering and Electrical Engineering Universitas Indonesia. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon and prosperous, warm, and spirit greetings. On behalf of the Department of Electrical Engineering and Computer Engineering Study Program, I am delighted to be here today to be the host for the visiting professorship lecture from Professor Keiji Kimura titled Parallelization for Non-Coherent Cache Memory Multicores by Oscar Compilers. This is the second lecture by Prof. Kimura that we already listened for the previous lessons last week about basic of memory hierarchy in recent multicore processors. So this lecture is conducted under the visiting professorship program from Universitas Indonesia. Before we listen to the lecture, please let me read again a short biography of Prof. Keiji Kimura. Prof. Keiji Kimura is a professor of Advanced Professor Architecture, Department of Computer Science and Engineering, Waseda University. He is the head of Kimura Laboratory, and also currently he is the director of the Green Computing System Research and Development Center at Waseda University in Tokyo, Japan. His research interests are parallelizing compilers, multi-core architecture, heterogeneous computer architecture, low power computing, and multi-threading methods. So maybe it is very interesting topic for all of us. And before we begin, I would like to remind to the audience that during the lecture, please make sure that your microphone is mute. If it possible, turn on your video. If you have questions, please type in the chat box, or you may also ask the question directly to Prof. Kimura later after the lecture. So without further ado, Professor Keiji Kimura, the floor is yours.
Thank you very much. Thank you for introduction. Let me start with the today's lecture. Just a moment. Okay, now you can see my slides. Okay, so today's topic is about the parallelization for non-coherent cache memory multi-core by ASCII compiler. And here we can see the keywords such as non-coherent cache memory. This is very curious because last week we briefly reviewed about the coherent cache memory, and we think this coherent cache memory is very popular in today's multi-core systems. But here, uh, we are now we are going to focus on this non-coherent cache. What is this? And what is the motivation? This is the important point here. And the second keyword here is Oscar compiler. Oscar compiler is a parallelizing compiler we have developed for 30 years uh, for 30 years. And this is started from by the Professor Kasahara. He is now Vice President in Waseda University, and he was also IWCS President in 2018. And there are important points. So again, our topic here is parallelization for non-coherent cache memory multi-core. And of course, this topic is based on the last week's topic, basic of memory hierarchy multi-core processor, likely cache memory, particularly cache coherency in multi-core and multi-processor systems. Okay. And please remember the basic idea of cache coherency firstly. So the idea of cache coherency is keeping the latest data for each variable in a system. And it means, in other words, a system does not allow multiple new data in a system. Only one new data for each variable in a system, each object in a system. To do so, the system try to invalidate the other object in the other cores when one core try to store the data in the cache. This is called as a cache invalidate based protocol. By invalidating all the copy of data in other cores, the system can keep only one data in the system, only one new data in the system. This is the basic idea. And note that when a system tries to keep this kind of coherence traffic like invalidation and cache miss operation traffic must be broadcasted in a system. Okay, this broadcasting mechanism is a problem, and we will see this problem later. Before focusing on parallelization for non-coherent cache multi-core, firstly, we will focus on the overview of parallel processing. Okay, because today's topic is particularly focusing on parallelization. It means how to accelerate a program by multi-core. After that, we will see the non-coherent cache optimization by the compiler. Okay. So let's start with the first topic. Maybe it will take nearly 1 hour for this topic, and after that, we will focus on this topic within the remaining 1 hour. Okay. So more concretely, firstly, we will see about the brief overview of parallelization, and then we will review the cache coherency, basic of the cache coherency, and then, as I said before, we will discuss about our motivation. Our motivation means why we need software cache coherency or non-coherent cache optimization by the compiler. Then I would like to introduce our technique, parallelization and cache coherence, cache coherence optimization by the compiler. Then I would like to explain the performance evaluation result on the multi-core. Okay. And during this lecture, sometimes I would like to ask several questions. And if you prefer, please raise your hand. Please chat your question and answers. Anyway, anytime. I'm very welcoming to have questions, discussions, and so on. I like interaction with the student.
Okay, okay.
Okay, yeah. So what is parallelization? Let me start from this topic. Parallelization. Parallelization is one of the program optimization technique. Maybe you have already studied about the programming on some kind of compilers like GCC or Clang or so on. And you have also studied about some optimization techniques by a compiler like code optimizations, some kind of sophisticated optimizations by a compiler. By employing these kind of compiler optimizations, our program can be accelerated. Thus, we can enjoy the accelerated program execution on our computer, our Node PC, our smartphone, and so on. And again, parallelization is one of the powerful optimization techniques of a program. One of the important motivation here is obtaining a faster and faster and faster and faster program. And what is parallelization? It means utilizing multiple cores, multiple processors in a system. And by orchestrating those multiple cores in a single program, we can expect to have more performance. How? Firstly, we must decompose a program into several tasks, then execute these tasks simultaneously on different cores. By doing so, again, we can obtain a faster program execution. How? How can we decompose program into tasks? We must, at that time, we must take care of data dependence and sometimes control dependence. What is the data dependence and control dependence? They are our next topics, dependence. So before going to these dependencies, I would like to ask simple questions. Have you ever made any kind of parallelized programs by, for example, pthread library, OpenMP, CUDA on GPU, and so on? How many students have you ever made parallel programs? Please raise your hand.
Yes, for participant, please raise your hand if you already do the parallel programming.
You can see the raise your hand button on Zoom.
Yeah. I think not yet.
Not yet.
Not yet. Students already do the parallel programming.
Okay, I see. Okay, let's go to the next topic.
Okay.
So you don't have to worry about this because in the first half of this lecture, I would like to give some ideas about the parallelization. Okay, but first, the basic idea here is very simple. Decompose a program into several tasks and execute them simultaneously. Okay, and to do so, each task must be safe when those tasks are executed simultaneously. It means those tasks must be executed independently. More concretely, uh, when we want to execute those tasks simultaneously, even though those tasks must give us correct answers. Correct answer. This is important point. First and correct execution are important points, of course. And in order to ensure this condition, we must take care of data dependence. What is data dependence? Generally speaking, task A depends on task B stands for the execution of task A depends on the task B, of course. What is the dependence here? The basic idea of data dependence, the fundamental idea of data dependence is task A uses the data generated by task B. In this example, this statement, the second statement, C equal to A minus D, uses a data A, variable A. And the result of this variable A is generated by the first statement, A equal to B plus C, of course. Of course, this statement must wait for the completion of this statement, obviously. So in this case, we say there is a dependence. More particularly, true dependence is there between these two statements. Okay, this is obvious and simple case. And and if there is no data dependencies, for example, if this statement write a data to, for example, variable f, like this, f equal to b plus c, and still this statement is c equal to a minus d, we can execute those two statements simultaneously because this statement does not use variable f generated by this first statement. Okay, this is an obvious case. But we should think about other situations like disallow and disallow. Why? Obviously, this third statement does not use data generated by the second statement C equal to A minus D. There's no C in this statement. But we must not exchange the order of these two statements. We still wait for the completion of task second statement when we want to execute this third statement. Why? Here, we can see this third statement overrides the variable a, which is used in the second statement here. Okay. When we exchange the order of these two statements like this, a equal to e by f. After that, c equal to a minus d. For this case, this order exchanged c equal to a minus d uses data a overwritten by this third statement. It means the answer by this second statement becomes wrong, incorrect. So we cannot exchange these two statements, or these two statements. So the fundamental point of the relationship between these two statements is overwriting a data used in the previous statement. Or we can say that this kind of relationship, like use A after that, modify A, overwrite A. For this case, we say this relationship as anti-dependence. Anti-dependence. Anti means anti-relationship between true dependence. Here we can see write and use relationship. For the case of anti-dependence, we can see use and like, use and define. So for this case, we say this is anti-dependence, and we cannot change the exchange of, we cannot change the order of execution of these two statements. There's still data dependence. And what kind of, how about these two statements? Both statements write data to variable A, okay, variable A. For this case, again, we cannot exchange order of statements. A equal to E by F, A equal to G divided by H. If we exchange the order of these two statements, assume that we have also other statements that will use the variable A. And now these two statements are exchanged. And the statement here using variable A uses long data, long result of A. So when we exchange the order of these two statements, succeeding statements have an effect, long effect of this exchange, by this exchange. So we cannot still exchange the order of these two statements. And it means there is a data dependence between two statements. So in this case, we say this relationship as an output dependence. So roughly speaking, when there is a data dependence between two statements, we cannot exchange the order of these two statements. It means we cannot execute those two statements simultaneously. Thus, we cannot enjoy the parallel execution of these two statements. This is a point. This is an important point of data dependence. Okay. In summary, when there is a data dependence, we cannot execute those two statements simultaneously. Those two statements in parallel. And when there is no data dependence, of course, we can execute these two statements in parallel. So when we want to make parallel programs, firstly, we can find data dependency in the program. And when there's no data dependence between among tasks, among program chunks, we can decompose those programs into several chunks or tasks and execute in parallel. This is the basic step of parallelization. Okay. And here we can see other terminology, RAW, WAR, and WAW. This is other naming of dependencies. RYW stands for the read after write. Read after write. Read after write dependence. WAR is, of course, write after read. Write after read dependence. This is the same as anti-dependence. Write after read. And output dependence is also called as WAW, write after write. Write after write. So sometimes we can say dependencies like RAW, WAR, or WAW. Okay. And the important point here is dependencies. Those dependencies are caused by variable modification, variable definitions. So variable definitions causes a state change in a system. This kind of state changing affects the execution of remaining tasks, remaining statements. So this is a fundamental point of data dependencies. By changing a system state, by changing a system status, it causes some kind of data dependencies. Okay. So by changing the state of contents of variable A, this statement affects. This statement have an effect of execution timing, and so on and so on. Okay. And here we can see a word true dependence. You should have questions. So this is just a true dependence. So other two dependencies are pseudo dependencies. Pseudo. It is true. Why? We can avoid these. We can resolve these two dependencies. We can resolve anti-dependence this and output dependencies. How? Can anyone answer this question? How can we solve anti-dependence and output dependence? I would like to give some one hint. We can modify a program. We can modify a program. For example, here we can see the anti-dependence between these two statements: C equal to A minus D and A equal to E by F. How can we eliminate this anti-dependence relationship? Can anyone answer? Okay, the next hint. I said there is an anti-dependence, but this third statement does not use a data generated by this second statement. But but writing this variable A code is anti-dependence. So how can we eliminate this anti-dependence? Can anyone?
Anyone can answer the question? Yes, please, Harditya. Maybe you can turn on your mic and answer the questions. Mikhail Arditya, please. Oh, Harditya.
Okay. Yeah, someone given an answer. Changing the position of A to C. Yes, exactly. I'm not muted. Okay. Okay. Very good. Very good. A to C. I think we should use the another variable than C because we use C here. But the answer is very good. Introducing other variable, like for example, k equal to E by F. Thus, this statement no longer defines the variable A, no longer override the variable A. So there's no anti-dependence here. Similarly, how can we eliminate output dependency between these third and fourth statement? How can you eliminate output dependence? The situation is here. This variable A is over this variable A is written twice by these two statements. And this causes output dependency. So how can we eliminate this output dependency? There's another variable maybe, of course, yes. Exactly, excellent. Very good. So for example, by introducing another variable like m, a equal to a by f, and m equal to g divided by h. So in this situation, variable a is no longer overwritten. So we can eliminate output dependency. So, okay. So for the case of true dependency, we cannot eliminate this one because uh, defined A is next used. But for the cases of anti-dependencies and output dependency, the uh, overwriting variables, overwriting a variable causes anti-dependency or output dependency. Okay, overwriting is a fundamental point of anti-dependency and output dependency. So by introducing other variables, we can eliminate these two dependencies. Thus, uh, we put true on true here for this true dependency or lead after right dependency. Okay, good. So even if we have anti or untopped dependencies in the program, we can solve these two kinds of data dependencies and we can have more parallel. Okay, so let's try these three cases. So the kind of data dependencies in each case, case 1, 2, 3. And what kind of data dependency in this case 1? Can anyone answer? Yes, please. Total dependency. Oh, yeah. Thank you very much. Thank you very much. Total dependence on what variable? What variable called data dependency? Yes, a variable A. Define A and then use A. So what kind? How about case 2? How about case 2? Yes, anti-dependence. Yes, thank you very much. Anti-dependence, excellent, excellent. On B. And how can we eliminate this anti-dependence in case 2? How can I eliminate anti-dependence? Could you give me some example for the program modification? Can it be equal another variable such as k? Oh, thank you very much. Excellent. Introducing another variable like k and keep the execution result of d divided by 3 to k, for example. And thus we can eliminate the anti-dependence. And how about case 3? How about case 3? This is a little bit difficult to answer, maybe. So how about case 3? Data dependence. Which kind of data dependence? Tool dependence. How and why? Okay, now, yes, the answer is okay, good. There is tool dependence. So defined variable is used here. And which condition causes tool dependence for this case 3? variable if m is equal to n, then it's the same variable. Excellent. Excellent. Yes. If m equal to n, same array element is modified and used. Thus, we must say that the data true dependence between these two statements. Otherwise, there's no true dependence. If m is not different from n, uh, different elements are modified and used. But this is the important point to think about the parallelization. If we don't have information about the exact number of m and n, we should think in conservative. We should think in conservative. M may be equal to n. We should we must have an assumption such that conservative assumption such that m may be equal to n. Thus, we must assume that the true dependence. Thus, in this case, we must not parallelize these two statements. But of course, if we have information such that m must not equal to n, there's no two dependence, and we can execute them in parallel. So the information, additional information such like array subscription are very important to investigate the parallelization. Okay, very good. So now we understand the data dependence among two statements. But only executing two statements in parallel is not enough to speed up, to accelerate the program, because most of execution time is spent in loops, spent by loops in the program. So we should focus on loops to optimize program. This is the fundamental rule to accelerate our programs. Firstly, we should expensive, time-consuming part of a program. And in most cases, generally speaking, in most cases, loops are time-consuming part because something operations are iteratively executed many times. So loops are time-consuming part in the program usually. So how can we accelerate the loops? How can I accelerate the loops in the program? The answer is decomposing a loop into several chunks and execute them in parallel. And of course, the important point to parallelize the loop is checking the dependency. So which part should we focus on the loop when we want to parallelize it? The answer is iteration, among iterations in the loop. We will see later. So this is the basic idea of loop parallelization. So assume that we have such kind of loop. And the idea is decomposing this loop into several chunks like this. Now, in this example, this loop is decomposed into 4 chunks. 1, 2, 3, 4. And execute those chunks in each core. CPU 0 execute the chunk starting from I equal to 0 to 249. CPU 1 execute chunk starting from 250 to 499. CPU2 execute a chunk starting from I equal to 500 to 749, and finally CPU3 execute the chunk starting from I equal to 750 to 1999 and 999. Okay, and in each small chunk, small answer is calculated like this. Partial execution, partial answer is partial answer for this part. Partial answer for this chunk is executed, and answer is now once stored in the sum 0. For this case, answer is stored in sum 1, sum 2, and sum 3 similarly. And after calculating sub answer, we can see barrier here, barrier function here. What is barrier? Barrier stands for the what a kind of synchronization of tasks. It means that the all CPUs wait for the finishing all tasks in all cores. For example, assume that CPU0 finish the partial calculation firstly, and CPU1, 2, 3 are still executing those their own subcalculation. So in this case, CPU0 must wait for the completion of CPU1, 2, and 3. Similarly, now CPU3 finishes. CPU0 and CPU3 CPU0 and CPU3 finishes their own tasks. But CPU1 and 2 are still executing. In this case, of course, 0 and 3 also wait for the completion of CPU1's task and CPU2's task. So this is a meaning of a barrier function, a role of a barrier function. We say this kind of waiting for other tasks as synchronization. Of course, there are other kinds of synchronization, but now we just focus on the barrier synchronization. Anyway, after this barrier synchronization, the system can ensure all tasks are finished. And after that, CPU0 collect the partial answers from other tasks. And finally, CPU0 can obtain the final answer by adding these two sub-calculations. So this is the basic idea of loop parallelization. Okay, again, one loop is decomposed into several chunks and execute them simultaneously, independently. And after finishing all tasks on all cores, all CPUs, answer is summarized if needed. Of course, we don't. Sometimes we don't have to wait for those kind. We don't have to think about those kind of summing up. For this case, each CPU can continue to execute next tasks and so on. Anyway, basically, in parallel program consists of two parts: sequential part executed on only one core, and parallel part like this. Oh, sorry. Execute some calculation on all cores and synchronization, and sometimes collecting sub answers. And sometimes sequential part is sequential part follows after the parallel part, and then sometimes parallel execution is occurred, and so on. Okay, so sequential parallel synchronization, sequential parallel and about synchronization. And in order to maximum our performance, our program execution performance, of course, enlarging a parallel part as much as possible. To do so, we must find the independent part by carefully checking the dependencies within the program. Okay, let's go back to this loop parallelization. In order to decompose one loop into these kind of 4 loop chunks, we must ensure these loop chunks must be executed independently. In other words, we must ensure there's no data dependence between CPU 0 and 1, CPU 0 and 2, CPU 0 and 3, and so on. More concretely, we must ensure all iterations in a loop must be executed in parallel. Okay. There are thousands of iterations in this loop, starting from I equals 0 to 999. It means when we want to execute this loop in parallel, iteration 0 and iteration 1 must not have data dependency. 1 and 2 also, 2 and 3 also. And in summary, all iterations must be executed in parallel by ensuring there is no data dependency among those iterations. So a programmer must ensure it, and this is very tough work. And from all the dates, compiler have done it. It means compiler tries to check the dependency among iterations in the loop. And if a compiler can detect the no dependency among iterations, compiler can make a parallel code for this loop. So how can a compiler detect a dependency among iterations? This is a basic this is the basic idea of finding data dependency among iterations. So let me start from this original loop for I equal to 0 to n. And each iteration, this loop body is executed. Here we put a label for each statement in the iteration from S1 to S4. And this is difficult to investigate for the student who studied this topic at the first time. So I unrolled this loop like this, starting from I equals 0 to 1, 2, and so on. 0, I equal to 0, I equal to 1, I equal to 2. For these cases, each subscript of each array becomes like this. For first statement S1, when I equal to 0, A0 equal to B0 plus C0, obviously. Then we can see at the second statement S2, Ci plus 1, we can see Ci plus 1. So when I equal to 0, this becomes C1. And this statement becomes like this: C1 equal to A0 plus D0 and so on. and blah, 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 blah. So we can easily check the data dependencies among statements and among iterations. For example, at the first statement, defined element A0 is used at the next statement, second statement, to dependence. Of course, at the second iteration, I equal to 1, the result of our first statement is still used at the second statement and so on. A1 equal A1 equal and equal A1, A2 equal and equal A2. Similarly, the result of the second statement is used at the third statement like this. Here and here, here and here. But it's okay when we want to parallelize this loop. So how about red arrows? Here, 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 so. We can see the defined array element C1 at the first iteration, zeroth iteration, is used at the first statement of first iteration I1. C1 here and C1 here. Define and use. Similarly, this C2 is also used at the I equal 2 statement iteration here. C2 and C2. And also we can see this array element C2 is overwritten here at the next iteration. C3 is overwritten here at the next iteration. A1 defined here is overwritten by the next iteration.
Ya, yang tadi tuh masalah.
Sorry? Question?
No, please continue.
Oh,
Please
okay.
continue.
And A2 is also overwritten here. It means there are true anti and output dependencies among iterations. Okay, among iterations. So we can find dependencies among iterations. So we can decide, oh, we cannot parallelize this loop. And we say this kind of iterations among this kind of dependencies among iterations as loop carried dependence. Loop carried dependence. And when a compiler or a programmer detect any loop carried dependence in a loop, it means a compiler or programmer must decide, oh, this loop cannot be parallelized. Otherwise, it means if a compiler or programmer cannot find any loop carried dependence, we can parallelize it. Okay. And the important point here is here we just focus on the array data structure and its subscriptions. Okay. According to the loop variable I, loop counter I, access to array elements are changed. And by checking these array elements, each array element, or by checking array elements according to the loop counter variables, we can check which array element are accessed in each iteration. And then we can find the loop carried dependence by checking the expressions in array subscript, like this: I plus 1, I plus 2, and so on. It means, okay, firstly, a compiler or a programmer must check the data type in a loop. And then next, we must check the array subscript in each array element. Then we can check loop carry dependencies among iterations. So basically, when we want to parallelize loops, we should those loops should have array data structures and some kind of regular access patterns. And more particularly, access patterns should have a relationship with loop counters, loop counter variables. So, okay, let's go back to the previous slides. Here, m equal to and d equal to n and so on, and assume that these statements are enclosed in a loop. It's difficult to say this can be parallelized because they use different variables. And one variable may have a relationship with loop counter, and another variable n may have no relationship with loop counters. So we cannot predict the access pattern for these two array elements, and we must decide the parallelization conservatively so that we cannot parallelize this loop. Or if these expressions can be represented by using loop counters, we can predict the access pattern. Such compiler, maybe a programmer can easily decide the parallelization for this loop. So in summary, when we want to parallelize a loop, let's focus on the data structure. It should be array data structure, and array subscript should be regular shape, which related with loop counter variable. By doing so, we can predict the access pattern. And access pattern, detecting access pattern is important to parallelize the loop. From this loop counter related array subscript, we can check the loop carried dependencies. So this is the point. So more briefly, we should say when we want to parallelize a loop, we should use regular access pattern program. Okay, so this is the this is the basic point of data dependency and related loop parallelization. So this is the important point. And now, so far, we focused on very simple programs, like only statement and only have regular access loops, regular access pattern loops. So how about control statements, like if statement or while loops, and so on? In order to parallelize a program, we should also focus on the conditional branches as well as data dependencies. For example, we can see the one simple program. If C1, then C1 equal to F. And after that, C2 equal to G. And assume that F and G, function F and G have no data dependencies. And obviously, C1 and C2 are different variables. If there's no if statement, we can easily detect parallelization. C1 and C2 can be executed in parallel. But this program has if statement here. For this case, the execution of this statement C1 equal to F depends on the result, evaluation result of this if C1 statement. If C1 is true, this C1 equal to statement, it will be executed. Otherwise, this is not executed. So again, the execution of this C1 statement depends on the result of this condition C1. We say this kind of dependency as control dependency. So this is also related with the loop execution. For example, sometimes we see that kind of code in a loop. If some kind of condition becomes true, loop is finished. Okay. It means next iteration, the execution of next iteration depends on this condition. Okay. Similarly, we can see while loop example. This loop executes during this count variable is true. It means next iteration, the execution of next iteration depends on this variable. Okay. This is a very big problem to parallelize the program because, let's go back to this slide. Assume that there is an if statement, if break statement in this loop. We cannot parallelize it because if loop continue condition is broken, or during this loop chunk, loop is finished by executing a if break statement. We must not execute this loop chunk, and this loop chunk. Okay. The execution of remaining iterations depends on the condition of this if break statement. And if break statement is true and the loop is stopped, remaining execution of remaining iteration makes long answer. So it means we must not parallelize this kind of loop. It means if there's a control dependency within a loop, we cannot also parallelize a loop. Of course, we cannot parallelize this kind of loop. So in summary, in order to parallelize a loop, we must take care of control dependence as well as the data dependence. So in summary, if we want to parallelize a loop, firstly, we must check the data dependence, loop carried dependence among iterations. And also, the number of iterations to be executed must be fixed at least at the start of the loop. So it means, in this case, n must be fixed before executing this loop. N is of course n can be of course variable. Maybe 1, maybe 10, maybe 100, maybe 1,000. It's okay. They are okay. But 10, 100, 1,000, the exact value of n must be decided at least before the execution of this loop. So they are important point to parallel loop. And fully parallelizing a program by a compiler, it's a very important techniques and technology, and it's very convenient, but sometimes it's difficult. So hybrid approach, giving a hint to a program and a compiler, and according to these hints given by a programmer, compiler parallelize the program. This is a very popular approach. And OpenMP is a very popular parallel programming model for this approach. This is very popular and easy to try. This is a parallel application programming interface for C, C++, and Fortran. And a programmer gives hint to the compiler by inserting compiler directives. What is compiler directives? We will see later as an example, as some examples. Anyway, we firstly write an ordinary program in C, C++, and Fortran, and insert some hint information in the program. And the compiler can ignore them. By ignoring them, that program is executed as ordinary sequential program. And if compiler can understand the meaning of compiler directives, compiler parallelize it according to the inserted hint information. And basically, OpenMP is focusing on the loop parallelization. It also supports other kind of parallelization, but many people have been enjoying loop parallelization by OpenMP programming. And we will see the shared memory model. This is a kind of popular organization as we studied last week. All processor cores share one memory. And currently, many compilers support OpenMP like GCC and Clang LLVM, so you can easily try it. And please check this slide later by yourself due to the time limitation. And this is samples, very simple samples for OpenMPs. And this programmer statement, programmer line, it's a given hint directives, hint information by a programmer. Programmer OMP stands for the hint directives, hint information for OpenMP compiler. And the parallel for stands for the parallelize the following loop like this. And by giving this information, compiler parallelize this loop. And the correctness of the parallel execution must be ensured by a programmer. Okay, so programmer must ensure there is no loop carrier dependence among its iterations in this loop. And this just parallelize a loop, just decomposing a loop into multiple chunks evenly. And if some kind of collective operation like all summation in a loop, a programmer must specify this kind of annotations, reduction, plus colon sum. It means in this loop, this some variables will be accumulated by other operations. And it means after parallel execution of each subchunks, the partial summation must be corrected, like this example, this statement. Okay. Anyway, by just inserting those kind of easy, simple directives, we can enjoy the parallel execution of our multi-core processor, the multi-core systems. And assume that we must write our own parallel program like this. It means decomposing a program code into multiple chunks by our hand and insert barrier functions by our hand and summing up partial result after barrier functions and making required threads by hand. All those are very tough works by ordinary programmers, and we should remove those kind of tough works. And compiler must have a responsibility of these tough works and open imperialize it. And this where the variable is also a very important point to understand the parallel execution program, but due to time limitation, I would like to skip this slide. And anyway, I said again, I want to say again, currently we can easily try OpenMP by using ordinary GCC or Clang LLVM compilers. So please try by yourself. Okay. And by using this kind of OpenMP compiler, we can easily enjoy the parallel programming, but it's still tough work. We should imagine a compiler fully parallelize a program automatically. And this is our motivation of development of Oscar compiler. And I will talk about the Oscar compiler soonly. Anyway, let's check this discussion point. Let's discuss what kind of program can be parallelized and how. And I think it's a little bit tough work for you because you almost all of you have not have experience about parallel programming. But let's imagine what kind of programs are appropriate for parallelization. Can anyone answer?
Please, Indra.
Yes.
Oh, I think.
Please. So I said, it's programs that have no dependence. Yes, of course. And what kind of application area? What kind of application area is appropriate for parallel programming, parallelization?
Physics simulation?
Physics simulation. Very good, excellent. So what kind of physics simulation are you assuming? Looping a single data with no dependency, yes. It's program characteristics. So how about the application area? Physics simulation is very good. And physics simulation includes several what kind of area, like, well, okay. So in physics simulation programs, what kind of calculations are used? What kind of calculations are used? Or what kind of data structure. Calculating different collisions. What kind of collision are you meaning?
It's the interaction between two objects.
Oh yeah, very good, excellent.
They can make it for chunks,
Mm.
so they can calculate it independently in
Sure.
different part of the simulation.
Yeah, excellent. And physical simulation is very typical parallel programming target, and many of them use it. Many of them use matrix calculation, matrix multiplication, some kind of equation solving, or eigenvalue calculation, and so on. These kind of matrix calculations are very suitable for parallel programming, and many kind of parallel programming packages have been provided. So for many years, supercomputers have been used for calculating, executing, accelerating those kind of physical simulations. Okay, physical simulation, very good, excellent answer. So how about other application areas? Physics simulation, very good. How about rendering? Excellent. Rendering, excellent. Image, 3D image rendering, 3D image rendering, both are very good. For example, 3D image rendering are very typical applications for parallel programming, and also 2D image, manipulating a 2D image. Maybe you can easily imagine that kind of the Photoshop applications or other kind of graphics, what I say, painting applications and so on. Those kind of 2D graphics modification, 2D something applications or 3D something applications are very good for parallel execution. And the important point here is 2D space or 3D space can be thought as a set of dots, set of pictures, set of pixels. And many kind of 2D image rendering, 3D image rendering can be thought as a set of pixel manipulations as they can be executed parallel. So graphics area is also very good parallel application, parallel programming application target. Excellent. And there are many kind of other application areas, but physical simulations and graphics are two of the most popular target for parallel programming. Very excellent. And common characteristics for these two areas are many calculations, or same kind of many calculations are processed for many data. Okay, for matrix multiplication or matrix calculations and graphics rendering required many kind of calculations for each element, each pixels. This kind of characteristics is very important for parallel programming, very efficient for parallel programming, parallel execution. ので excellent. Okay, so let's go to the compiler optimization. As I said, OpenMP is a very good popular approach for parallel programming, but we want to we want to ask a compiler to fully parallelize the program automatically. So again, for according to this motivation, we have developed the ASCII compiler. This is automatically parallelizing compiler we have developed for 30 years. And the second half topic here is non-coherent cache control by our OSCA compiler. So let's review the coherency first. So this is the typical organization of shared memory type SMP multi-core or multiprocessors. Here we can see two PEs or processing element. It means a set of CPU and cache, two cores, and one shared memory connected by interconnection. It's some connecting module. As we studied last week. And now at the initial point, a shared memory has variable x and its value is 1. Okay. And during the program execution, those CPUs have same value for variables x as data 1, value 1 in their cache. Cache 1 has value 1 for data x. And also for this CPU, for this cache, x is kept in this cache as value 1. This is okay. At the next time, this CPU 0, writes new data 2 to variable x. And this becomes old data. And the system, this core puts an invalidate signal to this interconnection. And all cache connected to this interconnection check the invalidate signal and check its state. And for this example, this cache listens the invalidation signal for this variable x, and this value 1 becomes invalidated. And after invalidation, when this CPU want to load data for variable x, this new data held in this cache is once written back to the shared memory, and this cache loaded from main memory, shared memory, okay, invalidated. And if this x is requested again, this x is written back and loaded. So for these processes, firstly, again, at the writing point of new data x equal to 2, invalidation signal for x is broadcasted, okay, broadcasted. And when this cache want to have a new data x, the cache miss request or reading data x request is also broadcasted. So writing at the writing time and read miss time, broadcast requests are occurred. In order to make coherency in the system, those broadcast requests are needed for cache coherency protocol, invalidation-based cache coherency protocol. So this is the basic point to understand the cache optimization technique by the compiler. So at the motivation here is we want to omit this kind of automatic hardware cache coherency communication. Why? This is a very convenient mechanism because we don't have to take care about this kind of coherency mechanism without notifying them. We can write the program correctly. Okay, hardware can safely make a coherency, ensure the coherency. It's convenient, but it requires some kind of complicated hardware. And the scalability for this coherency mechanism is not so good. In order to obtain more and more performance, we want to have more and more cores, 100 cores, 1,000 cores maybe. But this kind of cache coherency mechanism has little scalability. This scalability means when we want to put more and more cores, overhead caused by this hardware, coherency hardware becomes large. Large area, large silicon, large power consumption. And also, control overhead. It means the control delay becomes longer. So if we want to put more cores to obtain more performance, we want to omit this hardware coherency mechanism. But of course, it causes a small problem. Someone must have a responsibility of coherency in the system. Now, we don't choose the hardware option. So the next option is software cache coherency. Instead of introducing hardware cache coherency mechanism, we choose software cache coherency mechanism to obtain the scalability for future many cores. This is a motivation. Of course, coherency control, cache coherency controlled by programmer is very tough work. We don't want to ask a programmer to do this kind of very tough work. So our option is doing everything by compiler. Okay. And how I said about the loop carrier dependency. And it means compiler or programmer must check the loop carrier dependencies among iterations, and it means data use and define scenario must be checked before the program execution. Okay. And if compiler do it, parallel compiler can do it. It means compiler can understand the data usage, which data is defined where, and which data is used where. Compiler can detect them, and then compiler can parallelize it. And it can be also used for cache coherency control, because important point of cache coherency control is data is now defined, and other used data must be invalidated. And the data must be written back to and read from main memory. It means when other core have a request to read it, the requested or the owner cache must evict the data to the main memory. In order to obtain, in order to realize this by software, software must understand that when data is defined, when data is read, when data is used. And again, parallelizing compiler can have information such kind of data usage. When data is written, when data is used. By utilizing this information, compiler can appropriately insert the invalidate operation, data eviction operations, and so on. Thus, we can omit the complicated hardware from a complicated mechanism of cache coherency from hardware. And also, we can realize the software cache coherency by the compiler without programmer's effort. This is the basic motivation and idea. And when we focus on the cache coherency-based software, which kind of problems must be focused on? There are 2 points. The first one is stale data handling. Stale data is old data. When the data becomes old, the new data is defined somewhere in the system. Other data in other cores become stale data. Basically, stale data must be invalidated. And of course, invalidate-based hardware coherency mechanism invalidates them automatically by the broadcasting message. And the software must take care of it for the non-coherent cache mechanism. And the second point is force sharing handling. Force sharing, do you remember? The force sharing situation is independent data is located on the same cache line. So one data is invalidated, other data is automatically invalidated, even they are independent. This is a force sharing problem. And I will talk this situation later. So we realized this software coherence control techniques in our parallelizing compiler, namely OSCA compiler. So OSCA compiler includes several parallelization techniques, but here, please remember the role of this compiler, such that decomposing a program into tasks, like loops, like subroutine calls, and so on. Taking care of data dependencies and control dependencies. And after decomposing tasks, OSCA compiler place these tasks on available processor cores appropriately, along with appropriate synchronization operations like barrier operations and task-to-task one-to-one synchronization operations. Anyway, the important role of OSCA compiler is firstly analyze data dependencies and control dependencies, and the result of data dependencies is also used for the cache coherence control code. And exploited tasks from a program is appropriately located on each task by ensuring the task execution order by inserting appropriate synchronization code. And this is the image of a decomposed task from a program. And each edge shows one of data dependency or control dependency. It means defined data here, for example, defined data in this task 5 is also used in this task 7. Define to data 3 is used at the, by this task 6. Define and use. Define and use. Oscar compiler can detect this kind of information. Okay. So how can we avoid, how can I solve these two problems by utilizing the data dependence analysis result or data flow analysis result? Data flow analysis is a kind of data usage analysis. Again, which data is used in where in the program, which data is defined in the where in the program, and so on. So let's think about the stale data problem. This slide shows an example of a stale data situation. And this is initial status. This is shared data. A, B, and C are shared by these two cores, two processors. Okay. And at the processor one executes this statement B equal to A. B equal to A. This is okay. But in this, by this statement, these data are copied into the private cache in this processor 1. And assume that these variables are located on the same cache line. Anyway, 0, 0, and 10 for 1A, B, and C are copied here. After that, processor 0 modified the data A to 20, 0 to 20. So once this data 0, 0, 10 for variable A, B, and C are once copied here, processor 0 to cache, private cache, and A is modified to 20. And here, processor 0 to cache have 20, 0, and 10 for A, B, and C. And note that this is non-coherent cache organization. No invalidation signals is occurred. So P1's cache still has data 0, 0, 10 for variable A, B, and C. So this data 0 for variable A becomes stale. So after after this situation, when the system, both software and hardware, have nothing to do to take care of it. When PE1 use data A, like this, C equal to A. Now data C has a copy of data A. Processor 1 uses the stale data 0, stale data A of 0. And it is copied to C. This is incorrect. Correct answer is here. This value must be used. This value must be used. And the correct answer for this statement is here. But without without taking care of the stale data handling, this situation is occurred. And this is wrong. So again, when ordinary hardware is used, at the modification time of A equal to 20, this statement is executed. Invalidated signal is broadcasted, and this 0 is invalidated. This line is invalidated, and when C equal to A is occurred, executed. This PE1 request read miss request on the system, and this data is written back to the memory automatically by the hardware, and this updated data is read by this P1, and this C equal A is executed correctly. But again, now we assume the non-coherent cache hardware, and this must be done by software. How? After modification of data A here, write back operation, write back instruction is inserted by a compiler. And after that, flag variable is set. It means this data A is written back by processor A, sorry, processor 0. This indicates the completion of this write back. And at the P1 side, before using updated A, this checking code, flag checking code is executed. By executing this do-while loop, this P1 can ensure the completion of this write back request, because after this write back operation, this sync flag becomes 1. And after this flag is written back to the memory, this loop can load the new sync flag 1, new sync, updated sync flag. After checking this becomes 1, this P1 read updated data from memory, written back data A from memory here. But the compiler must take care of the flag write back and invalidation here. This is also firstly written into the cache, and this flag variable must be main memory by inserting this write back operation like this. And this flag is once read from memory. This flag is also copied into the cache. If this is still 0, still not 1, this loop still reading stale data repeatedly from a cache. So once this sync flag is read, this must be invalidated. This invalidation self-cache data is represented by this annotation, self-invalidation sync flag. By executing this instruction, sync flag variable on the cache is invalidated. And after that, this at this statement, this P1 can read flash data from a memory. Thus, eventually, this flag assignment and write back operation updates the sync flag variable on the memory, and eventually this do while loop can check the flash data, updated data. And after that, self-invalidation for data A is also executed. And stale data on the cache for this data A is invalidated by this statement. And at this function call, this function can read the flash data of data A defined here. Thus, by combining write back instructions and self-invalidation instructions, software can ensure the data invalidation and data write back, and resulting in coherency in the system. So this is the basic idea. And the compiler insert these kind of write-back synchronization and self-invalidation appropriately by utilizing data-defined and data use information obtained by the data flow analysis, data dependence analysis. So okay, now we can solve the force sharing. We can solve the state data problem. So what about the force sharing problem? Force sharing assumes that independent data A and B are located on the same cache line, and this is the initial state. Initially, they are set like such that 0 and 0. Okay, and this data A is used and modified by processor 0, and this data B is used and modified by processor 1. But again, processor 0 does not use data B. Processor 1 does not use data A anymore. So assume that such a situation. Now at P0, A equal to 1, and A is modified like this. And P1, B equal to 20 is executed. Here, cache line on this P processor 1 is modified like this. They are executed independently on the non-coherent cache hardware. Is this correct? Of course, this is incorrect situation, incoherent situation, because on this cache, on this P0 cache, B is still 0. This is stale data. On this P1 cache, A is still 0. This is also stale data. So they must be merged. How? There's no way to merging data on this system. Because cache management is done by cache line unit. When this is written back to the shared memory, main memory, my memory values are 10 and 0. When this is written back to the main memory status, main memory situation is 0 and 20. Both are in correct situation. Correct situation is 10 and 20 for A and B, respectively. But they cannot be merged. So this is a force sharing problem. Remember that the case of hardware coherency mechanism on the ordinary processor, multi-core processors. Once A equal 10 is occurred first, this is firstly executed. The data copied in this cache is invalidated. Okay. And once after that, when B equal 20 is executed, this updated line is written back to the main memory, and this P1 read updated data, and successfully this modification B equal to 20 is merged into updated A to 10. Firstly, when this is firstly executed, this is written back, and then this is read, and 10 and 20 are merged. Similarly, when B equal to 20 is executed, this is invalidated. And this is executed. It is when A equal to 10 is executed, this line is written back, evicted to the main memory, and this is read by P0 when A equal to 10 is executed. And also, this A equal 10 is merged into the B equal to 20. They are serialized but successfully merged. But for the case of non-coherent cache architecture, again, they cannot be merged. So how can we solve this problem? The intuitive answer is assign different cache lines for independent data. For this case, assign one cache line for data A, assign another cache line for data B, like this. So they are perfectly independent. So P0 and P1 can be updated independently. We don't have, they do not take care of other side modification. And by utilizing data dependence analysis and scheduling information, compiler can understand which processor modify which data when, and the data location. So when independent data are accessed simultaneously, compiler can decide, okay, those data must be located on different cache lines. And the compiler can insert such kind of declaration. Roughly speaking, they adjust the cache location, cache line location by inserting this kind of attribute notation. And successfully, they are aligned, they are located on different caches. So this is an intuitive idea, fundamental idea of solving force sharing. The important point here is independent data must be located in different cache lines. This is the basic idea. Of course, sometimes this is a difficult situation. There are difficult situation to assign the independent data on the independent cache line, like divide or array elements into different processors. This is one simple example. So now array A, which has a 36 element, is in the program, and the loop utilizing this loop is parallelly executed. For example, 0 to 70 and 80 to 36 elements are executed independently. And the compiler must ensure those data, those elements modified by those processors must be placed in a different cache line. But if we think about the different variables, compiler can easily locate different data on the different cache line, but this is the same data, same array data. How can we ensure the no fault sharing problem, no fault sharing situation? The answer is one element for one line, one element on one line, like this. By utilizing another dimension for array. Thus, we can assume that in this architecture, one line for 4 integer elements. Okay. One line can contain 4 integer elements. And by introducing this one additional dimension, we can ensure one array element for one cache line. Thus, a compiler can divide data array elements in anywhere in the loop. By chopping the array elements here, we can ensure one non-fault sharing situation. By chopping here, we can also ensure the non-fault sharing situation. So this is one solution when a compiler must deal with array elements. And there are other kind of ensuring non-fault sharing situation, but the important point here is by adding additional array elements or additional dummy data like this. We say this as pad, or by inserting pads to ensuring non-fault sharing situation. We can solve the fault sharing situation. So there are another interesting cases, but the this is a time limitation and the topic complexity. I would like to skip these remaining slides. Anyway, the important point here is by okay. In summary, in order to ensure the coherency, cache coherency by the software, we must focus on two problems. The one is stale data handling, and the second one is fault sharing problems. And in order to attack stale data handling, a compiler must insert write-back instructions and self-invalidation instructions and synchronization appropriately. And by utilizing data dependency analysis information, compiler can insert them appropriately. And in order to avoid fault sharing problem, compiler must adjust the data location. More concretely, compiler must ensure one data for one element, basically, or one data chunk, and no fault sharing situation. By doing so, compiler adjusts the data location, or sometimes insert pads appropriately. In order to do so, compiler also utilizes the data dependence analysis information or data flow analysis information, which data is written, which data is used when, where in the program. By utilizing so, compiler can adjust the data location appropriately. There are two basic ideas to solve the stale data handling and fault sharing situation. And the important point here is how can we reduce the hardware overhead by introducing this software cache optimization. This is a discussion point, but I would like to give some hint. Of course, hardware must have some kind of complicated hardware to ensure the cache coherency. More concretely, cache coherency hardware must generate the cache control communication request, like invalidation request, read missed request, write missed request appropriately by the hardware by monitoring the read and write situations appropriately. And this causes a complicated hardware and low scalability due to the many traffics, many communications to ensuring the cache coherency. But software cache coherency can reduce the hardware complexity as well as the communication cost. What kind of communication cost? Again, hardware must generate the invalidation request when the data is updated. And also, invalidated data is, after invalidating a data, when a core wants to request the updated data, it must generate the read missed request and write missed request, and they must be broadcasted for all cores. All core cache must listen these requests, invalidation and missed request, and give response appropriately. They are the causes of the overhead for low scalability. and they must be solved by our software cache optimization techniques. So I would like to discuss here about the time limitation. I will skip here. Sorry. So I would like to show some performance evaluation result. We use popular benchmark application programs. And in order to evaluate this compile optimization techniques, we used RP2 processors. This is developed by our all previous collaborative project with industrial companies supported by Japanese government. At that time, we developed 8-core embedded processors. And at that time, fully coherent hardware is difficult. Making a fully coherent hardware is difficult at that time by the industry. So industrial engineers decided 4 cores in a system can be coherent. It means 8 cores are divided into 2 clusters, 2 4 cores clusters. And within the one cluster, coherent can be ensured by the hardware. But in order to, when we want to use 8 cores, fully 8 cores, coherent cannot be ensured by the hardware, and the software must ensure the cache coherency. So we developed our cache coherent software cache coherent optimization by in the OSCAR compiler and evaluate it. And we can compare our software technique and hardware technique at 4 cores. So this is the block diagram of our 8-core multiprocessor. 4 cores. Among these 4 cores, cache coherency is ensured by the hardware. Among these 4 cores in the cluster 1, hardware cache coherency is hardware cache coherence works within these 4 cores. And this is the evaluation result. Each label shows the executed program, equal program, out program, and so on. And this is the MPEG-2 encoder. This is the very popular video encoding program. And others are array-based numerical applications. And each bar shows execution normalized speed up utilizing only 1 core, 2 cores, 4 cores, and 8 cores. Okay. And each bar shows the speed up comparing with the sequential execution on with ordinary execution. 1 core execution. 1 core execution. So, of course, parallelization was done by OSCAR compiler. So OSCAR compiler generated the parallelized code and executed the same program on the same hardware with cache coherency mechanism and hardware cache coherent and non-coherent cache mechanism. And the blue bar shows the ordinary parallelization by hardware. And as I said before, hardware ensures the coherency up to 4 cores. So blue bars 1, 2, and 4 cores can be executed on hardware cache coherency mechanism. On the other hand, red bars shows a non-coherent cache mode. It means OSCAR compiler ensures both parallelization and cache coherency by the software. So in this case, we can utilize all 8 cores. So 8 cores, for 8 cores, only red bars are here, here, and here. And firstly, we can find OSCAR compiler can exploit the scalable performance improvement for each program. For example, uh, around 3 times performance evaluation, sorry, 3 times speed up for this HAMR programs over 3 times speed up for utilizing 4 cores for MPEG-2 encoders. And more importantly, software cache coherency by the OSCAR compiler also can successfully work for 8 cores. It means 8 core can obtain the better performance than 4 cores cases like this. So it means OSCAR compiler can utilize 8 cores, fully utilize 8 cores, and successfully speed up with software cache coherency and automatic parallelizations. And more interestingly, for some applications, for example, CG, HAMR, RBM, EART, and eQuake, focus on the 4 core cases. Non-coherent mode can obtain better performance than hardware cache coherency cases, comparing with hardware and software on CG program. Software cache coherency can have better performance comparing with hardware cache, such that 37.1 versus 37.1 versus 33.4. And for these cases, 3.19 versus 299 cases. So it means by avoiding false sharing by the software, OSCAR compiler can obtain better performance. Also, OSCAR compiler software cache coherency optimization can also reduce the redundant coherency traffic, like invalidation and broadcasting misrequest. By combining these two effects, OSCAR compiler can obtain the better performance even comparing with the hardware cache coherence mode. This is the spec result. Okay, I will skip some analysis, but due to time limitation. But in conclusion, in this lecture, we review the basic knowledge about the parallelization in terms of the dependencies. And after that, I introduced the basic idea of software cache coherency and performance evaluation by the OSCAR compiler. And in summary, we can have a better, achieve the scalable performance improvement for the case of non-coherent cache mode on the hardware, even using the 8 cores. And more interestingly, for some applications, comparing with hardware cache mode, OSCAR compiler with software cache coherent optimization can achieve the better performance. And this can be used, we think this can be used for future many cores, future low power and high performance many core systems. And that's all my talks. And if you have a question, please let me know. Discussion is very, I prefer to have the discussions. Yeah, thank you very much.
All right, thank you, Professor Kimura, for your interesting topic and presentations. Now, actually, we already spent our time, yeah, because the limitation is 3:30. But maybe I will give opportunity to the audience for 2 or 3 questions. If there is any questions from audience. Okay, is there any questions?
Yes, please.
Oh. Okay, Aditya, please.
I want to ask question about page 12 and 13. When the array with I is equal to 0, so the element of the array is I minus 1. So the size of the array is minus 1. It is compiler error or not?
You mean that sorry, I'm array elements of I minus 1 or array elements of A minus 1? Sorry?
In page 12 and 13, Professor.
Maybe can you open the slide number 12?
Sorry, which slide?
Slide number 12, Professor.
Slide number
12.
12. Here?
Yes.
Yes. Sorry. This should be starting from 1. Yeah.
So it should 1, not minus, right?
The I minus 1 for
I
the
minus 1,
source element of A.
they use I minus
Yes.
1, and this is starting from 0. Yeah, sorry, it's a mistake. It should be started from 1.
Oh, okay.
Oh, okay. Thank you, Professor.
Yeah.
Okay, from Evan Heberts.
Okay, I have a question by chat, and I want to ask about the compiler in C. C has many siblings like C++ and C sharp. Are they using the same compiler or slightly different compiler or a totally different compiler? Oh, okay. Okay. Good question. Yeah. So other programming language similar to C. The question is about the other programming language similar to C. In the case of C++, we can employ the same kind of techniques for C++ programs because many kind of important characteristics can be shared same as C. Actually, we are now extending our compiler to support C++, and partially it's okay. Of course, C++ has very different characteristics of C comparing with C, such as object-oriented and virtual function invocation and so on, but they are okay, basically okay. As long as the compiler can analyze, can trace the data usage, this kind of object-oriented characteristic can be supported. Anyway, in summary, we can what I say, we can use the same compiler for C and C++, basically. Actually, we are now extending our compiler to support C++. And about the C sharp, it's very challenging topic because C sharp and also Java language have very dynamic behavior at the runtime. Dynamic behavior means which function will be executed or which data object will be accessed. It's very difficult to detect by the compile time. And also, C Sharp and Java program relies on the exceptions heavily. And exception is implicit behavior in the program itself. And this is very difficult to handle by the compiler. So summary, basically parallelization itself can be employed for C# programs, but fully automatic parallelization for C# and Java language are challenging. So many, for example, many compiler designers or compiler researchers have developed parallel Java compilers, parallel C# compilers with hint directives, hint information. A very good question. And also, some researchers also try to runtime parallelization. Of course, runtime parallelization will introduce some kind of heavy overhead. But if there are some kind of good trade-off between runtime overhead and runtime parallel execution speed up, it can be also feasible solution. A very good question.
Okay. Thank you, Professor Kimura. One more question maybe from audience. Okay. I think.
Can I?
Oh, please,
yeah,
please, Andy.
Okay. Firstly, let me introduce myself. My name is Andi Farhan. I just want to ask something that I from the that I from how to speak.
Mau nanya? Ditunggu.
From what I know, there is some program that do not support multi-core processing. When those programs use this Oscar compiler, do they have benefit from it? So that they can support multi-core processing. Thank you.
Yeah, thank you very much. Thank you for your question. So if those programs are written in C and Fortran, we can try it. And maybe those programs are especially relies on the array data structure. I think Oscar compiler can parallelize it successfully. So it depends. To be honest, it depends on the program behavior and program characteristics. But if they are written in C and C Fortran, we can try it, and maybe we can successfully we have successfully parallelized many kinds of C programs, and I think Oscar can possibly parallelize them.
Oh. Okay.
Thank you very much, Professor.
Thank you.
Okay. Thank you for the audience and for Prof. Keiji, for Prof. Kimura. I think because the time is very limited, so we pass our ends today. Thank you very much for your presentation, and I would like to invite Dr. Ratna, Dr. Putri Ratna, to give closing statements to represent our program study. So, Dr. Putri Ratna, please, the floor is yours.
Okay, thank you. Good day. On behalf of everybody here and the Universitas Indonesia, I would like to express my highest gratitude to Kimura Sensei for your generous willingness to have your expertise and teaching on a very highly competent subject in the state of the art of computer architecture. I'm very sure you have enhanced our knowledge and motivate many of us here, especially the students, to explore further in the area. Kimura Sensei, thank you very much for everything. And 今日は本当にありがとうございました。本当はこっちに来ていただいて講義をしていただきたいんですが、こういう状態で、でも次の機会には来ていただこうと思っていますので、これからもよろしくお願いいたします。そして笠原先生によろしくお願いいたします。よろしくお伝えください。今日は本当にどうもありがとうございました。Thank you very much.
Thank you very much.
Okay, thank you, Dr. Putratna. So this is our end for this sessions, and thank you very much again for Prof. Kimura. We hope we can continue our cooperations. Maybe for the next time we can share our knowledge again or anything else. So thank you for also for the audience for participate in these sessions. And the time I give back
Maybe
to.
you take the picture.
Oh yeah.
Yes.
Okay.
Don't forget.
Okay. Sorry. I forgot. So maybe for all of audience and so please activate your camera so we can get the absence. Everybody already active the camera?
Okay.
Okay, I will take for the first page. 1, 2, 3. Okay, next we have a seventh page.
Okay.
Okay, so please patient. Be patient. Okay, this is the second page. 1, 2, 3. Okay, and next the third page. 1, 2, 3. Next the fourth. 1, 2, 3. Next the fifth. 1, 2, 3. For the sixth. 1, 2, 3. And the last page. 1,
Finally.
2, 3. Okay, finally this is the last page of our participant. Okay, thank you very much for the audience, for the Prof. Kimura.
Yeah.
We can see next time.
Yeah,
Please,
this is my honor.
Thank you.
I give back the session to Dr. Prima.
I think that's all.
That's all.
Okay, Prof. Gede.
Okay.
So thank you very much,
Thank you
Kimura
very much.
Sensei.
Thank you very much.
And see you again.
Thank you again.
Okay, see you
Thank
next
you.
time.
Arigatou
Thank you.
gozaimashita, Kimura sensei.
Thank you.
Thank you.
Okay, thank you.
Arigato.
Arigato, Kimura sensei.
Arigato. Thank you. Thank you.
Arigato, Kimura sensei.
Konnichiwa wa arigatou gozaimasu.
Arigato.
Sayangannya Bu Ratna nih. Okay, so I will end all the session.
Okay, thank you.
Okay, thank you very much.
Okay.
Thank you
Okay,
very much.
Thank you.
see you, Kimura Sensei.
See you.